So my plan is to finish the material for the exam on Wednesday. So yeah, we'll get there. There are only two topics left to cover. One is kind of like how to find domains of functions of two variables, which is what we'll do today. And then how to find limits, which is what we'll discuss on Wednesday. So let me tell you first about functions of two variables. So this is really where we start going more into like what you would think of more like calculus in the traditional sense of the word. Like before, we have been discussing like, vectors and lines and planes, but that's to a large extent like a preamble to, you know, to the other stuff we're going to do. Like now we are going to talk about like limits, derivatives, max min problems, things of like more like the stuff that you saw in Calc 1, for example. So the first thing that we need to discuss in this case is that, like what functions of two variables are, because there are like some interesting things that happen with respect to like the functions of one variable. So let's just remember, like, just as a reminder, what are like functions of one variable? Well, so there were functions like this, right? Maybe you had like x squared, or you could also have like e to the x, or like you could have more complicated things like x plus natural log of x. Well, and then you could keep going. The important thing about any of these, right? Like for example, y equals x squared and y equals e to the x, they're both defined for any value of x, right? So both make sense. For any value of x. Right, but if, for example, if you look at the last one, well, you can only talk about the natural log when x is strictly positive. So already this one, like, as a formula in terms of x, only works, right? Or it's only defined for x positive. So, even like already in Calc 1, like depending on the particular function, the domain, which is what we'll talk about, is not necessarily the number line, right? Like it could have been like some intervals. But regardless, of what happens there, the idea is that the domain, sorry, not the domain, the graph, right? Like if you have a function of one variable, the graph looks like a curve. So you have something like this. Oh, maybe like the function is not defined, or it is defined, but it has like a jump, right? Like a discontinuity, what you would say. So maybe the function looks like this, but the important thing is that in terms of the graph, you just get like a curve on the XY plane, right? So the graph is a curve. Okay. Um, Now we want to talk about functions of two variables. So let's say now you have a function of two variables. So they're like, there could be like analogs of this. So like, instead of like the function depending just on x, you would write something like f of x comma y. So one could be, I think the one that I wrote like the first day of class, like just x squared plus y squared, right? That would be like a possibility. Another option would be kind of like a version of the exponential. You could have something like e to the x plus y. Okay, and this already will show you like a couple differences when you start writing like different formulas for the function. So for example, if you look at the first, if you look at any of these, right, in the same way in which you write before, like y equals f of x, y equals f of x, y equals f of x, here it will make sense to write something like z equals f of x comma y, z equals f of x comma y. So let me write that down for each of them, right? And then the other thing you could do, just by analogy, is like if you just think of this as an expression in terms of x and y, you can start asking, oh, what values of x and y I can plug in that give me like an answer, right? Like that give me like a sensible answer. So like maybe it's easier to start with x squared plus y squared. If you think about x squared plus y squared, like you can basically feed any value of x and y into this expression, and that does make sense, right? Like, so you could do -1 squared plus 3 squared, or square root of 2 squared plus pi squared. So these actually will be defined for any values of x and y, and the same happens for the exponential. So if you take two numbers, if you take two numbers and you add them, you can take the exponential of that number. In fact, it just ends up being e to the x times e to the y, right? Because of like the formulas of the exponential. So definitely these two, right? These two formulas or functions will say make sense for any values of x and y. So this makes sense. Okay, so just to kind of prepare the stage for what we want to do today, like you could draw the XY plane, right? And I could like I kind of like could paint or could just like indicate like which sectors of the XY plane are allowed. So for these two formulas, like you could just choose the values of x and y anywhere. So I'm just kind of trying to say here that any value of x and y works. So here any value of x comma y works. So what I'll say in a few minutes is like the domain is just like the entire plane. So the domain is the plane. Okay, but maybe it becomes more clear if we try to compare this with, say, for example, this one. So let's think about this case. So you have something like ln of x plus ln of y, and you like almost think about it like in terms of like a calculator, right? You want to enter that into a calculator. So you want to ask what values of x and y can you choose to get like an actual output, right? Like you don't want to get error on the calculator. Let's just leave it like that. Yeah. Right. So what you need is like the natural log to make sense for each of these two pieces individually. So what you want is x to be positive, and you also want y to be positive. You want both of those to be true at separately. So for x positive and y positive. Is that making sense? Is that plausible? So what I'm saying is that if you choose a value of x that's positive and a value of y that's positive, then this doesn't make sense. The moment one of these two is negative, then you're done. Like there's even zero also would be problematic because you cannot really take ln of zero, or like you actually say it's like negative infinity, but like we want kind of like finite values if you like. So what that means is that if you were to draw if you wanted to represent like visually what values of X and Y you can choose, like now you cannot color the entire XY plane, right? You essentially cannot color only the first quadrant, right? So because you need X to be positive and Y to be positive. So my point is that if you choose like values of X and Y that are in the first quadrant, then this is good to go. You can feed in that into this formula. But otherwise, that wouldn't make sense. So here you want to say that the domain, you would like to say that the domain is the first quadrant. Is that making sense? So far, so good. Okay, and the last one is similar but a bit trickier than the other two. So you have to ask now, you have the product of two numbers, right? And when could the natural log of the product be okay? Yes.
When X and Y are both positive or negative.
Right, good. So you do need, like, that's the thing, right? Now you want this to be positive, right? So you want XY to be positive. And so you ask, oh, when is that true? Well, that is true when both have the same sign. Like that's a better way to say it, right? Either both positive or both negative. So need same sign. So both positive. So what does that mean? When both are positive, that's just like the first quadrant again, right? When is it that when are both negative on the third quadrant, right? Like that's when that happens. So this function, I'll show you the graphs in a second. For that, we do need GeoGebra because those are difficult to plot. But this function makes sense if you choose values of X and Y in either of these two quadrants. Okay, so the domain would be the first and third quadrants. So this, like the interesting thing here is that, these two expressions don't quite match because if you remember maybe from the properties of log, like ln of a times b is like ln of a plus ln of b, like you probably have seen like these properties, right? And I mean, this is a correct property whenever like, A and B are both positive. Because otherwise you could say something like, ln of 2 is like, let's say, or let's put it like 6, right? You could say, well, ln of 6 is like ln of -2 times -3, right? And obviously you cannot just split that as a sum, right? So this is wrong. So, like the natural log properties hold when like, both like in this particular case, when like both quantities are positive. So what I'm trying to say is that like these functions, if you just think about it in terms of like the identities for a line, you might say, oh, aren't they the same functions? But you can see here that they're not the same functions because their domains are different, right? The second will make sense for both the first and third quadrant, and the first one will only make sense on the first quadrant. So it can be tricky, like, sometimes to distinguish those two cases, but you have to kind of like, like whenever you apply the properties for ln or exponential functions or things like that of that sort, you do need to make sure that the expressions are everywhere defined. Otherwise, you could like just write silly things. Okay. Yes.
So the log properties don't hold for in this case?
They do hold as long as you plug in both X and as long as X and Y are both positive, then it does hold. It's just that which is so this, like, it's still true that, I mean, this is still true. Or let me write it here. So this is true as long as both X and Y are positive, right? So all that I'm trying to say is that you do have to be careful, because like, yeah, otherwise, like if both here could be negative, and when you multiply them, you get something positive. So that obviously there, like the property wouldn't hold. So all that I'm trying to say is that they're just, these two are not quite the same function everywhere, because on the third quadrant, one is defined, whereas the other is not. But yeah, on the first quadrant where both are positive, then yeah, like there's no difference between the two formulas, if that makes sense. Okay, so what I'm showing you here is kind of like, what are the values of X and Y that are allowed to plug in, and that's what is called the domain. The graph is a little bit trickier. So the graph is actually what, like, the graph involves plotting not just like the input, but also the output. So for that, we do need a little bit of computer assistance. So it's better to just show you how these examples look like, and then we can discuss more generally what the graph is supposed to be. All right, let's do it. Move over here for a second. Okay. Okay, so for example, this is the graph for x squared plus y squared. So what that means is like here, like choose your favorite point for your favorite values for x and y. That gives you like a point downstairs. So for example, here I'm choosing like what, like 1, -2. So I choose like net 1 for x and -2 for y. And so I square them and then add the answer. So I would do 1 squared plus -2 squared. So that gives me 1 plus 4, that's 5. So here, above this point, you should imagine that there's like the value 5, right? So the graph like of a function incorporates also the value the function takes. So what ends up happening is that since this expression makes sense for any values of x and y, so you have to imagine that for any value of the xy plane, you can kind of look up and you would see like the value the function takes. So in this particular case, like the function ends up looking like the paraboloid that we had discussed before. But the important thing is like when you think about the graph, you're thinking about like the value, not just like the input, but also the output. So you're thinking also like about the values that the function can take. So but the important, like, like the thing to notice here is like kind of like this shape, this surface, which will end up being, will be is everywhere in all quadrants, because like this expression is defined for any values of x and y. But if you take something like, let's just change it to the other one that we were talking about, like ln of x plus ln of y. I don't know, hopefully it can plot this. I didn't try it before. Okay, cool. So it's actually hard, like if you take ln of x plus ln of y, then you can, like you can see that the surface, like the graph itself, let's look at it from this angle. Like it looks better. Oh yeah, it looks way better. The graph only, only for points here, you can see something upstairs, or downstairs, depending whether the function is positive or negative. But there are like complete areas of like the xy plane, which are all these 3 quadrants where you cannot evaluate the function. So there's nothing to give, like there's no output to give, right? So if you think about the graph in this case, like the graph only kind of lives on top of the first quadrant and nowhere else is to be found, right? So here, like you can see that the domain, which is what I was drawing on the board, would be the first quadrant. So the domain is here, and the graph, which is actually like the function, like the output of the function, just kind of sits on top of the domain. That's one way to think about it. And then if you change, hopefully this also makes sense, works well. If you change this to ln of x times y, so you see now, like the third quadrant is also fine now, because you could have like, is what we were talking earlier. You could have 2 negative numbers and multiply them, and that still will give you something where you can take the natural log. So the point here is that the domain again is the first and third quadrant, so that's where like the graph is like above the domain in a sense. But and now like kind of like the second and fourth quadrants are excluded. But like the important thing is kind of trying to make is that one thing is that domain, right? Which is on the XY plane, and then the other thing is like the graph, which kind of lives all in space. So let me write that down to make that distinction more clear. So is that making sense? So what I'm trying to say, and this will turn itself on. So. So what I'm trying to say is that, and for like this, we'll only do for now for functions of two variables. So for a function of two variables, what is the domain? The domain are the values of X and Y, and the values or the points X comma Y, where the expression makes sense. So that refers to a region of the XY plane. So this is going to be for us a region of the XY plane. This is always so so what I'm saying in here is that you have like the XY plane and you have some region. I'll actually show you like in a second, like examples where the region is a bit more interesting. So. So what like the domain here means is that if you choose, well, the way you should think about it is that if you choose XY values which are inside this yellow region, then the expression for the function makes sense. And if you choose something outside the allowed region, then you cannot make sense of the function. Okay, it's undefined. Whereas the graph, and what is the graph of the function? So what the graph does is it keeps track of the domain plus the value of the function. So this also takes into account the values of the function. Into account the value of the function. So it is a point like X comma Y comma f of X1. So just to make it more concrete, say if I take something like z equals X comma X squared plus Y squared. So if I take a point downstairs like X comma Y, the point on the corresponding point on the graph kind of lives here and is X comma Y, but you're also recording the value of the function. So then the third entry would be the value of the function. So it would be X squared plus Y squared. Okay, so say this is like, I don't know, this could be 2, -1, So this would correspond to the point 2, -1, 5, which is the one I was discussing earlier. So the graph keeps also like shows you the value that the function takes. But the important thing pictorially, like because I'm more interested about like difference in terms of the pictures. So the difference in terms of the pictures is the graph like requires like the z-axis. So the graph requires the z-axis to, if you wanted to visualize it. And it also gives you some sort of like surface in space and corresponds. So in general, how this looks like, think like the easiest way to think about the graph is becomes like sort of like blanket, meaning that you have like a point x comma y here, and the corresponding point on the graph is x comma y comma f of x comma y. So again, this always kind of is like the domain. So the domain is always on the xy plane. And the graph is always like kind of like in space. So it's everywhere in space. So the thing for practical purposes, what you'll be asked to find is the domain, not the graph, because the graph involves like figuring out how the equation looks like, and that's like a way more difficult problem. So what we'll learn today is more like how do you find domains, okay? But it's important to keep in mind those distinctions. So what happens, the reason why we're focusing with functions of two variables is that, say, for example, if you had like a function of three variables, then you can no longer visualize the domain. Because if you think about it, for a function of three variables, then the domain requires a value for x, y, and z, but then the graph itself requires a fourth, like, requires a fourth axis, which is where like the output would go. So the graph of function of three variables cannot really be visualized that easily. So that's why we're focusing on functions of two variables, because you can kind of make pictures for everything. So let's do some more examples. Um, Here's another one. Okay, so what does this mean? It means like what values of X and Y can you plug in and this still makes sense? So for example, what if you try to do something like f of 1 comma 1? What should f of 1 comma 1 be? That should be 1 minus 1 squared minus 1 squared, right? So you should get root of -1. And I should, this is like a good point, like to insist that you should forget about calc 2. We don't do imaginary numbers in this course. So like for us, this really does not exist. So there's no answer for us in this world. Like, we only care when everything has like a real value. So like this is undefined for us. So you could say that's I, but just pretend like you never saw that, right? So you would say, oh, this is undefined. So we want to think of this as undefined. So another way of saying is that this should not be in the domain. Okay, so we don't want this in the domain. So one is not in the domain. Because we cannot make sense of this. Well, again, it's for again our purposes. Whereas if you take, for example, like something like f of 0, comma 0. Okay, that one is easy, right? Like it's just 1 minus 0 squared minus 0 squared. And that's perfect, right? That's just the square root of 1. And here we're always treating like this, the positive square root, so that's just 1. Okay, so this does make sense for us. So we would like to say that 0, 0 is in the domain. So again, like asking for the domain is just asking which values of X and Y you can plug in where you get like an answer. So if you remember for a square root, since like we really don't want things that involve I or it's like analogs, like for a square root, what we want is like the stuff inside the square root to be non-negative. Okay, then like we don't have to worry about anything. So for we want because the moment you have something inside the square root that is non-negative, then you can take a square root in the normal sense of the word and you get like a value, right? So we would like to say that the domain consists of all the points x, comma, y that satisfy this inequality. So the domain are all the points okay, so that's kind of like what the domain consists of. The thing is like that on its own is not that useful because how does that look like? That's really what you would like to know. Because just saying, oh, there are all the points where this makes sense, it's kind of almost circular. Yeah, of course, but I want to understand this a little bit better, right? So the question is like, is there a way to know what this does correspond to a shape on the XY plane? That's what I'm trying to say. Like this inequality gives you some sort of shape on the XY plane. Does anyone know what the shape is? Yeah.
That's like a circle with filled in.
Okay, good. So just to make that more clear, like, you could move the x squared and the y squared to the other side of the inequality. Right? And if you look at it that way, then this does look more like the equation of a unit circle, right? But because it's like greater or equal to, that's where the filling comes in. So what you end up having here is like the unit circle with the interior included. So it's essentially the unit, what you would call like the unit disk. So the domain is really the unit disk. And now this like actually, it's a lot more like concrete because it's saying if you choose a point inside the unit disk, then this expression makes sense. If you choose a point outside the unit disk, then there's nothing to be done with it. Okay, so this actually becomes like a more concrete way to think about the domain, rather than just saying, oh, it's just 1 minus x squared minus y squared greater or equal to 0. Yeah, that's okay, but that's not as interesting. So what we're kind of trying to do, come up with is more like a picture of what's about what the thing should look like, instead of like just like finding the correct algebra for it. Is that making sense? I'm about to tell you like a way to know how to these things look like. So that's like the next step, to show you, like, give you like a method for like plotting or drawing these regions. But let me just to, you know, kind of like nail down this point, like. So what I'm saying is that if you take something like the square root, I think you can edit and enter it. Okay, so that's the graph of the function, right? So like again, the graph includes the values of the function. So that's why you get like a surface in space. But if you look at you know, at the graph, it is only making sense above the disk here on the plane. So the domain is the disk itself, and the graph kind of like incorporates the values of the function. So it looks like maybe it's really like a half a sphere, like the northern hemisphere. Of like the unit sphere, essentially in this case. But like the important thing is again, like the distinction between the graph, which is like this thing in space in 3 dimensions, versus the domain, which is just the disk. So we are kind of like more interested in the domain stuff because that's easier to sort out of actually determining the graph. For the graph, it's just like better to just think about plotting it or something like that. So, but again, the important thing to notice here is like this like surface, like the red surface, is only above points inside the unit list. Okay. So it really all boils down to, as you'll see, what will happen in general to find the domain is that we'll get some inequalities, and it all boils down to drawing those inequalities. So that's what I'm about to write for you now. Like, how do you draw inequalities? How to draw inequalities on the plane. So it's basically 2 steps, and I'll show this again with a different example. But it, basically to draw an inequality in the plane, what you'll draw is like the equality first. So you will draw, step 1 is to just draw the equality. Which will be a curve on the xy plane. So this will be a curve on the xy plane. And then this curve, this is step 2, the curve divides the plane into regions. Curve divides the xy plane into regions. And by choosing a random point from each region, you check whether the inequality is satisfied or not. By choosing a random point from each region, you check whether the inequality is satisfied. Check. Okay, so let me do an example to illustrate this idea. See if we have a nice one here. Yeah, let's use this one. Let's see. Okay, so what does this mean? Again, you're trying to find what values of X and Y you can plug in where this makes sense. So because it's a fraction, there's something that should be kind of more like immediate. And maybe the natural log part is a little bit more complicated. But there's something that whenever you have a fraction cannot be allowed, right? So what happens with a fraction?
X times Y has to be greater than zero.
Well, it doesn't.
And not zero.
Right, not zero, yes, correct. So definitely, whenever you have a fraction, division by zero is problematic. So independent of anything else, the first thing to notice, so first observation, like for first condition is that you cannot have x, y can't be zero, right? Because it's in the denominator. And then you ask, well, when is the x times y equal, like, when could that happen? Like, for that, you just need one of the two factors to be zero, right? The moment x is zero or y is zero, you're done, right? So the issue, so what that means is that, x can be zero. Or let me just say it, let's say it in a more like straightforward sense. So x equals zero is not allowed, right? Because if x is zero, then you're done. Like the denominator becomes zero. When is x equal to zero, that's the y-axis, right? So all the y-axis is problematic in this picture. So y-axis is not allowed. And by essentially the same logic, y equals zero is not allowed. And so when is y equal to zero, that's along the x-axis. So the x-axis so just to draw like a preliminary picture, because this is all so far like the information I'm getting from the denominator. What I'm trying to say is that you want to think of the y-axis as a bad line. So this is bad, and you also want to think of the x-axis as being bad. So, let me put it here, bad. Bad. So the idea is like, don't even think about putting like a point that is in either of these two lines because like everything gets ruined. So that's still not enough because we still have to see what happens with the natural log, right? But the idea is that whatever the domain is, it will ignore the x-axis and the y-axis because either of those gives you issues. Is that making sense? Think about this. Um, okay. And now we can come to the numerator part, which is L, a natural log, right? So it's the same, similar to what we were discussing before. Like you have a natural log, and a natural log can only make sense when the thing inside the logarithm is positive, right? So because of the logarithm, we need y minus x squared to be positive, okay? Is that okay? And then the question is, how does that, okay, so that's the inequality, but then you can ask, how does that look, right? How does this look on the XY plane? That's essentially what this is supposed to address. So how does this look? So the idea is that to draw the inequality, right? This is an inequality. So the step is just to draw the equality first. So let's just put this like as an equal sign, right? So what is the equality? So step one is to draw the equality. Well, the equality is just replacing the inequality by equals. So you put y minus x squared equals to 0, and that is something you should know what it looks like, right? Because that's just a y equals x squared. And that's like a regular parabola, right? So that's easy to like understand. So like the first step, what it says is just draw the parabola that you're getting in this particular case. So you just draw the curve. That's why I said that it was a curve. Okay, so you draw a curve on the XY plane and you see like this kind of divides the plane into two pieces, one kind of inside the parabola, if you want to call it like that, like, and the other outside the parabola. Okay, and then what you're supposed to do is like, in step two is to test each region with a random point. So for example, so you see like there's region one is this one, region two is that one. So let's take a point from region one, which what is a point here? Like, for example, 2,0 for sure is inside the parabola, right? So what happens with 2,0? Is the inequality satisfied? Sorry, 0,2, I'm like wrote it, I flipped it. So this is 0,2. So you ask, oh, does this point satisfy the inequality? Yes or no? So what happens when you do 2 minus 0 squared? That's just 2, which is positive, right? So that means that the inequality is satisfied. So inequality. And so that means that the cool thing is that any other point that you had chosen inside the parabola would satisfy the inequality. So that's how this works. So you can either color it or make happy faces, whatever you like. I'll just make some happy faces, meaning that any point that I chose here, if I choose a random point inside the parabola, then like the inequality is satisfied. So those are kind of like where the domain, that's essentially, very soon you'll see like that's where the domain is going to be working. And then let's choose something like, in the other region. So for example, just to give you like an idea, like you could put like 1, -1. Okay, what happens if I put 1, -1 here? So this is like the other region, right? So if I do, now y is -1, and then you have to subtract 1 squared, right? And that gives you -1, -1, so that's -2. And that's clearly not positive, right? Like, so this violates, right? Not. This is false, right? It's not true that -2 is greater than 0, so it is not satisfied. So and like the cool thing is that, again, like the nice thing about how this works is that there's nothing special about this point. If I had chosen a point here, or a point here, or a point here, or a point here, like the inequality would have been violated. So all the region outside the parabola is kind of problematic. So again, like it's up to you, but like you can put like sad faces or whatever. So this is all bad. So the domain is just the stuff inside the parabola. Not forgetting, that you cannot have the y-axis as part of the domain. So the actual domain kind of incorporates both pieces of data. So for this problem, the domain let me draw it like this. So the domain has to be inside the parabola, but then you can just like, you can put it in words or like, color it. You can say this is excluded. And so let me just put something like this to say this is excluded. And actually the parabola itself is also excluded because along the parabola things become 0. And that is not possible because we cannot have ln of y equals 0. So you can also say that the parabola itself, the parabola is also excluded. So the domain is just the inside of the parabola minus this part of the positive y-axis. So it's just the inside of, or the what's called like some like the interior also. Interior of the parabola minus a positive y-axis. Is that making sense? So like in general, like, that is basically the idea of how the domain questions work. You do have to analyze each piece of the formula and ask where does the formula make sense, and that's how you kind of start like eliminating regions from the XY plane. So the point is that only if you choose values in the regions that are colored yellow, you can evaluate the function. So like the function, like the graph kind of lives on top of these two half parabola, a half solid parabolas, however you want to call it.
What is the parabola itself also excluded?
Oh, right, good. Because this is when y equals x squared, right? But what happens when y equals x squared? If you go back here, this would become ln of 0. And then it's just because we don't want to try to define. I mean, again, like you could say ln of 0 is negative infinity, but you don't want to get into those technicalities. So we do want like the answer to be like an actual finite number, if that makes sense. Basically, the answer is more algebraically because there was a strict inequality here. So whenever there's a strict inequality, you exclude the curve. And if it had been greater or equal to, then the curve itself is fine, if that makes sense. So. And yeah, like the workshop, I think Thursday we'll have some more examples like this. Yes.
So could we have dotted the parabola?
Yeah, you could also have dotted it. I guess you probably dotted here. Yeah, that's like if you don't want to use that many words, yeah, you can dot it like I think here. So let me dot it. And I guess you could also have dotted the y-axis. It's kind of clear here that you kind of like saw that earlier, but yeah, like if you like, you can draw like a solid curve to mean that you're putting it as part of the domain, and as like a broken curve if you're excluding it. Is that okay? Any other questions so far, Sylvia? Okay, so that is, in general, like, how you have, like, these questions about finding a domain, work. The other thing that's very related to this is like the concept of a level curve. Let me see if I can explain that in the remaining minutes. Uh, So. I just noted that people have added to GeoGebra like a bunch more like animations of curves, which are kind of cute. Like there's an annoyed chicken here and a singing banana logo, which I don't know how you make it sing. But so, but actually the animation I had in mind, well, it's, ah, okay. So what's happening here? So imagine that you have a function like x squared plus y squared, which is like one that we have been discussing a lot previously. So if you look at the graph, you get like this salad bowl, this paraboloid, right? Now, the thing about the graph itself, if you think about it, that's what I've been trying to tell you, the graph actually lives in 3 dimensions, right? So the graph is kind of in space, like in 3D space. So, you can imagine back in the day, before computers or whatever, like iPhones, that you cannot like carry in a practical way like the graph with you, right? Like it's not so easy to, you know, keep with you like a representation of the graph per se. But and so you can think of this, oh, maybe this is like a valley or a mountain, something you're kind of like, move like trying to climb or like just moving along. So you want to understand like understand a little bit the terrain. Like actually, see if I can do it here. Yeah, no, this actually looks a bit better. Okay. So now it does look more like a mountain, right? So maybe you're somewhere in here. If you're thinking you're like on the mountain itself and you want to get to the top of the mountain. And so like you cannot carry with you like a map of the mountain or not in an easy way, but instead what you can do is kind of carry like a map with the level curves. So that's what we're trying to describe right now. So the idea of a level curve, which is similar, like, also to these weather maps, like on your cell phone, like, what a curve, the level curve will do for you is kind of represent all the points at the same height. Okay, so for example, if you think again of this as a mountain, what the level curve will show for you is all the points that have a particular value for the height. So here it's like all the points whose height is, well, let's say it's in miles, 2.2 miles, okay, above sea level or whatever. So what for this particular mountain, all the points at 2.2 miles above sea level looks like this circle that you see here, right? So instead of like looking at the entire mountain, you just like see like a circle here that represents like that particular curve. And for example, if you want like a higher value, right? Oops. Okay, so this is showing me, this is kind of like annoying because it's showing me all at once. But oh yeah. Oh, okay, it's like this animation is kind of like it was already decided done for the other one. So yeah, now it's better. So if you imagine like I'm starting to increase the height that I'm looking at. So as you increase the height, these circles kind of become of bigger radius, and that's what you see here in the animation. So I'm increasing the circle. So for example, the top circle corresponds to this point, and other circles correspond to, so here, like it could be like all the points where the value is 2.2 or all the points where the value is 3. But the idea is like each level curve just represents like a curve where the function takes the same values. So I think I have this other animation here. Yeah, this is oh, this one is better because it kind of shows. So, you have like another function like 4x squared plus y squared plus 1. So it still has like this mountain shape, well, upside down, just more like a valley or something like that. And so say I want to look at all the points at height 4.5. So all the points at height 4.5 is on sort of like ellipse, and it corresponds to this ellipse, right? And if you choose a different value for the height, 2.25, you choose a different value for the height, it corresponds to this ellipse, which corresponds to this smaller ellipse on the XY plane. So essentially, like the level curve, what it does is kind of like represent on the XY plane, like the places where the function takes the same value. So that means that and this is something you could imagine more easily to transport with you, right? Like you can carry like a map that's just this. And so you know that if you walk along this ellipse, like the function will have the same value. And if you walk along this ellipse, like the function will have a different another value. So another way to think about this is if you think of this function as temperature, that's saying that along this ellipse, the temperature is constant. And along this other ellipse, the temperature is a constant, just a different value for the temperature. And that's kind of what you get like on this weather app where they will show you like, with different colors, like the regions where like, the atmospheric pressure has this value or the temperature is going to be this value, et cetera, et cetera. So the level curve is just a curve where the function has equal values, if that makes sense. So let me draw like a picture for you on the board. So what I'm trying to say is that you have a level curve, which is so you have like the graph of the function f of x comma y. Let me see if I can draw something more interesting. So think of this as some sort of terrain. So maybe this is how the graph looks like. And then I want to know all the points. Maybe I want to know all the points where the function takes the value 3. So let me call that f of x comma y equals 3. So this is all the points where the function equals 3. Okay. And if you see, like, it gives you a curve on the graph, but instead of like drawing the curve there, like you just bring it down and draw like kind of like the shadow on the XY plane. So this is like the level curve. So in general, if f of x comma y is a function of two variables, a level curve of the function is what you get by equating the function to a number. Okay. Or let's say to a constant.
We make it the domain as map of all the level curves.
Right, exactly. So the domain in a sense is like all the level curves put together. Because like, if you're on the domain, you have to take a value somewhere. So yeah, kind of when you, yeah, if you patch them all, if you patch all the level curves, if you glue all the level curves together, you recover the domain. Yeah, that's a good way to think about the domain. Good. So let me do an example, in the remaining minutes. The level curves actually, they're really easy to find. You'll be given a function and you just equate it to a number that you were told to equate it. So here's like, an example. So I have this function of x and y, right? X plus y divided by x minus y. I have no idea how that looks like, right? I will show that to you in GeoGebra once we're done with this, with the algebra part of it. But then you could be like, oh, maybe there are points where, again, you could think about it as the height of your mountain, or also you could think about it as the temperature at a point x comma y. Those are the two most easy interpretations. So you could ask, oh, are there some values, are there some points where the height is 2 miles or where the temperature is like, well, that would be too cold, but too Fahrenheit, you know? So you can ask, what is the level curve? F equals 2. So by that, I'm asking, find all the points where the value of the function equals 2. Let me write it as f of x comma y equals 2. So we're trying to find all the values of x and y where like the function takes the value 2, or other points x comma y where the function takes that value. So what do? You just essentially solve for that equation. So you're trying to find when is x plus y divided by x minus y equal to 2, right? And that's the answer, but of course, like the answer that way is not too illuminating. So you have to play a little bit with the equation first. So how can you do that? You can multiply both sides by x minus y. You get x plus y equals 2x minus 2y. And so what does that give you? It gives you the 3y equals x. So y equals x over 3, right? Does that make sense? So that means this is a line, right? A very simple line. Passing through the origin. So then positive slope. So it kind of looks like this. So then what that means is that if you walk along this line, right? If you walk along this line, the function takes the value 2. Okay, so anywhere on this line, the value of the function equals 2. Does that make sense? And so the level curve in this particular case would be that one. So before I say something else, let me show you how that looks, and I'm almost done. So what I'm saying is that hopefully this, I hope this can be plotted because it's a little bit more tricky. Ooh, okay. It's okay. Okay, this is interesting, right? So this is the graph of this function, right? And so we're trying to find all the points where the height is 2. So let's just put c equals 2, right? So like I'm trying to like find these, like all the points where the height equals 2. Kind of you're seeing like a line up here, right? And that is the line, was the y equals x over 3. So if you plot y equals x over 3, which it won't be it will, you know. So like it's a little bit tricky here. Like, let me see if I can change the color. There's too much going on in this picture. Okay, so if you see, like, what this is saying is that if you walk, actually, let me put it from the positive z-axis. Okay, so if you walk along this line, which is y equals x over 3, that it is along this line where the value of the function is 2. So I don't know if you can see it. It's just there's this line, and that's where it intersects this plane at height 2. So that is what the level curve looks like in this particular case. It takes a little bit of imagination to, like, see it, because here, like, GeoGebra is plotting it as a plane instead of a line, but it's kind of the same. So, and, like, it's kind of like a fun exercise to find other level curves. So, like, if you wanted, like, to find the level curve z equals 4, it's going to be actually it's also going to be a line, but it's just like a different line. So you can kind of see, like, there's some line here, hidden here. And to find that, you just to find that, instead of, like, instead of putting equals 2 here, you put equals 4, and everything else is exactly the same, right? And that's how you would find a different level curve. The only thing before I finish with this is that when you plot the level curve, you do have to, in this particular case, you do have to exclude the origin, just because, like, this is not defined at the origin. So here, notice that I'm excluding the origin. So 0, 0 is excluded, since it's not part of the origin. So in general, when you draw a level curve, you do have to kind of just draw the parts that are inside the domain. But that's the only potential issue that this one has. Okay, so in general, for our purposes, usually the level curves will be either like lines or circles or parabolas, because those are kind of like the things that you know how to draw on the XY plane. So it's nothing more complicated than that. But like from here, like this was a line, but it was not super obvious, right? So you sometimes have to do a little bit of algebra to identify it. But beside that, everything else is exactly the same. Okay, so on Wednesday, we'll talk about limits, and that, as I was saying, like, will be the last topic for the midterm that we have on Wednesday of next week. So I'll see you on Wednesday. That sounds good.